Lesson: Feature Extraction and Object Recognition Models. Feature extraction and object recognition models are cornerstone technologies in the field of computer vision, enabling machines to interpret and understand visual information from the world. In the realm of AI implementation, grasping these concepts is critical for professionals aiming to design and deploy effective computer vision systems. At the heart of computer vision lies the challenge of enabling machines to discern and categorize objects within images, a task that requires robust feature extraction and sophisticated recognition models. Feature extraction is the process of transforming raw data into a set of characteristics or features that can be effectively used by machine learning algorithms. These features are essential for object recognition, as they provide the necessary input for identifying and categorizing objects within an image. Effective feature extraction captures the most relevant data while discarding redundant information, thereby enhancing the performance and accuracy of recognition models. Traditionally, feature extraction was performed using handcrafted techniques such as scale-invariant feature transform and histogram of oriented gradients. These methods focused on identifying key points and edges in images, relying heavily on domain expertise to select the most relevant features for specific tasks. However, these approaches often struggled with the variability and complexity of real-world images, limiting their applicability in dynamic environments. The advent of deep learning has revolutionized feature extraction, shifting the paradigm from manual to automatic feature learning. Convolutional neural networks, in particular, have demonstrated remarkable prowess in extracting hierarchical features directly from raw image data. By employing layers of convolutional filters, CNNs are capable of capturing increasingly abstract features at each successive layer, a process that mimics the visual processing pathway of the human brain. This automated feature extraction significantly reduces the need for manual intervention, allowing models to adapt and generalize across diverse datasets. Object recognition models leverage the extracted features to identify and classify objects within images. These models are typically trained using labeled datasets, where each image is associated with a corresponding class label. During training, the model learns to associate specific feature patterns with particular object categories, enabling it to make predictions on unseen images. The effectiveness of object recognition models is often evaluated using metrics such as precision, recall, and F1 score. Precision measures the accuracy of positive predictions, while recall assesses the model's ability to identify all relevant instances of a class. The F1 score provides a balanced measure of precision and recall, offering a comprehensive evaluation of model performance. Deep learning frameworks such as TensorFlow and PyTorch have become indispensable tools for implementing feature extraction and object recognition models. These frameworks offer pre-built modules and libraries that simplify the development process, enabling professionals to focus on model design and optimization rather than low-level implementation details. TensorFlow's Keras API, for instance, provides a high-level interface for building and training CNNs, offering functionalities such as automatic differentiation, optimization algorithms, and data pre-processing utilities. One practical application of feature extraction and object recognition is in the field of autonomous vehicles. Self-driving cars rely on computer vision systems to detect and classify objects on the road, such as pedestrians, other vehicles, and traffic signals. By employing CNNs for feature extraction, these systems can accurately discern relevant features from complex road environments, ensuring safe navigation and decision-making. In healthcare, object recognition models are used to analyze medical images, such as X-rays and MRIs, to identify pathological features and assist in diagnosis. CNNs have been successfully employed to detect tumors and other anomalies, often achieving performance on par with or exceeding that of human radiologists. The automatic feature extraction capabilities of CNNs enable these models to learn subtle patterns indicative of disease, improving diagnostic accuracy and efficiency. Despite their successes, feature extraction and object recognition models face several challenges in real-world applications. One significant issue is the need for large, labeled datasets to train deep learning models. Acquiring and annotating such datasets can be time-consuming and expensive, particularly in specialized domains. Transfer learning offers a viable solution to this problem by leveraging pre-trained models on large-scale datasets and fine-tuning them for specific tasks. This approach reduces the amount of data required for effective training, making it accessible for professionals with limited resources. Another challenge is the interpretability of deep learning models. The complexity of CNN architectures often makes it difficult to understand how and why a model arrives at a particular decision, raising concerns about transparency and accountability. Techniques such as GradCam and Lime have been developed to address this issue, providing visualizations that highlight the regions of an image that most influence the model's predictions. These tools enhance model interpretability, offering insights into the decision-making process and building trust in AI systems. The integration of feature extraction and object recognition models into real-world systems requires careful consideration of ethical and societal implications. Bias in training data can lead to discriminatory outcomes, particularly in applications such as facial recognition and surveillance. Ensuring fairness and inclusivity in AI systems necessitates diverse and representative datasets, as well as robust evaluation frameworks to detect and mitigate bias. In conclusion, feature extraction and object recognition models are fundamental components of computer vision systems, offering the ability to interpret and understand visual information with unprecedented accuracy. The transition from manual feature extraction techniques to automated deep learning approaches has opened new possibilities for AI implementation professionals, providing powerful tools and frameworks to tackle complex challenges. By leveraging platforms such as TensorFlow and PyTorch, professionals can develop and deploy sophisticated models that address real-world problems in various domains. However, the successful application of these technologies requires careful consideration of data requirements, model interpretability, and ethical implications, ensuring the development of fair and transparent AI systems.